Hello everyone, this is Pookie Code, and in this video, we're going to look at Neural Networks Explained Part 7, where we will look at feed-forward using the matrix notation. So, let's get started. Okay, so let's say we have this neural network. So, two nodes at the input layer, two nodes at the second layer, and then one node as the output layer. And then we have, for example, weights 1 minus 2 to the first hidden node, then weights minus 3, 2 to the second node from layer 2, and then 5 minus 4 minus 1, 0 plus 3, biases and weights, all that good stuff. And we're going to use ReLU as the activation function. So if you recall, ReLU of x is equal to 0 if x is smaller than 0, and x if x is bigger equal than 0. So an equivalent definition is that ReLU of x is equal to max of 0 and x. Why is that? It's because when x is smaller than 0, max of 0 and x returns 0, right? And when x is bigger than 0, since x is bigger than 0, then max of 0 and x returns x. And this is the definition of ReLU, so that's good for us. Alright, so now we're going to try and input some data, some inputs to the neural network. So let's assume that I have x1 equal minus 1 and x2 equal 2. Then if you remember the vector notation, if you look at the previous video, which was part 6, matrix and vector notation, you'll see that the input layer can be represented as a vector of minus 1 and 2. And then we'll have the layer number 2, which is just basically going to be the weight times their respective input, and then you're going to add the biases, and you're finally going to activate. So how does that work? So you'll see that in the layer number 2, we're going to do 1 times this, and then minus 2 times this, plus minus 3 times this for the second node, and then 2 times this for the second node. Then we're going to have to add the biases. So plus 3 for the first input, and then minus 4 for the second input in the second layer. Alright, so this just gives us minus 5, 7, and then you add the biases as I told you, so plus the vector 3 minus 4, and this is vector addition, which gives us minus 2, 3. We then need to activate it using the ReLU activation function, and so we just do ReLU of that vector minus 2, 3, and if you recall, ReLU of x is equal to max of 0 and x, therefore the minus 2 just becomes a 0, and then 3 stays the same because it's bigger than 0, which gives us the vector 0, 3. Then the output layer, it's going to be 5 times 0 plus minus 1 times 3. Why? Because here you're just going to do 5 times 0 plus minus 1 times 3. And then you have to add the bias, which is of 0. So we have to do ReLU of that. So ReLU of the vector with only one element, minus 3, just gives us 0. So something that's very, very awesome of that is that you can express all of this feed forward using just matrices and vectors. So if you recall, we've seen that at the layer number 2, when we multiplied the weights with their respective inputs, we did 1 times minus 1 plus minus 2 times 2, which is just basically doing 1, the weight here, times plus the weight here, minus 2, and then you multiply by the respective inputs, so minus 1 and then 2 here. And then you're going to do the weight minus 3 and the weight 2 times the respective input, minus 1 and 2. So this can be expressed as a matrix multiplication. So our weights are going to be expressed as a matrix of the form 1, minus 2, minus 3, 2. And if you notice, this is just actually the coefficients that you multiply that are all in turquoise or whatever you call that color. So we're just going to do the example with the same weights we had. So when I multiply the weights with the input vector, I'm going to have 1 minus 3 minus 2, 2, multiplied with the vector minus 1, 2. And so if you recall the previous video where we did matrix multiplication, we can do matrix multiplication by putting the right element on top and the first element on the left, and then we're just going to do the first row with the first column and then multiply like that, and then we're going to do the second row in the first column and multiply like this. So this gives us 1 times minus 1 plus minus 2 times 2, which is what we want here. And then we're going to have minus 3 times minus 1 plus 2 times 2, which is also what we want. And this matrix multiplication gives us the same vector that we wanted, so minus 5, 7. And then we're going to add the biases, and remember that when you're adding two vectors, it's just vector addition. So basically you're just going to add, after you multiplied weights with their inputs, it's going to add the bias vector, which is going to give us the correct answer again, and we need to activate it. So we do ReLU of that. And as we knew, the shorthand notation for ReLU for functions is that when you do a function to a vector, it's the same thing as we implicitly mean that you take the vector and each element inside you apply that function. So now we're just going to define a few variables so that in our future videos we can understand how they work. So I'm going to define W of n as the weight matrix at the layer n. And W1 is just going to be the weight between the inputs and the next layer. So it's not an exponent, it's not a power, it is a superscript. So it's just a letter on top. And then I'm also going to have bias, the bias vector, with the superscript n, and it's going to be the bias vector that is added to the next layer after n. So you're going to see how it's all going to be clear. So basically, we're now going to look at the vector A of n, and it's actually just a vector representing the values of the layer n. So basically it's ReLU of the weights times your input plus the bias. And we're also going to use, because you'll see in the internet that they use A and X interchangeably. So whenever you see the vector X with a superscript n, it also means the same thing as A of n. So that's good to know. And we're going to refer as Z to n with the vector is the unactivated values of the layer n. So only the weights times its input plus the bias, without the ReLU, without any activation function. So if you have this neural network here, the same one, I have as input minus 1, 2. So therefore I have the vector x1 is equal to the vector A at the layer 1, which is equal to minus 1, 2. I have the weight matrix is equal to 1, minus 3, minus 2, 2. Then I have the bias vector at that layer is going to be 3 minus 4, because this bias vector is used, it's going to be added to the layer after 1, which is the second layer, and that's correct. Then we're going to have Z of 2 is actually equal to W1 multiplied with vector X1 plus B1. And this gives us the vector the matrix multiplication, and you add the bias. And this gives us the vector minus 2, 3, and this is the unactivated version. So we need to activate this with the ReLU activation function. And this gives us ReLU of Z vector superscript 2. So ReLU of that, since minus 2 is smaller than 0, this becomes up to 0, so which gives us the vector 0, 3. And then we're going to proceed again with the next layer. So Z3 is equal to W2 multiplied with the vector X2 plus B2. And this gives us the vector minus 3. And we need to activate that again. So we have X3 is the same thing as A3, you know. And you just do ReLU of Z of 3, which gives us ReLU of minus 3, which is just 0. So we can now write down the formulas for how to calculate a feedforward. So we know that at any layer n, Z of n is equal to the weight of the previous layer multiplied with the input of the previous layer, and then you add the bias at n minus 1, because this is going to mean that it's going to be the bias that you add at the n minus 1 plus 1 layer, so n layer. We also have the vector x n is equal to ReLU of Zn or An, same thing, and that's pretty normal. So the activated input is equal to the activation of the inactivated layers. And we're also going to have, if you substitute, we have that x of n is equal to ReLU of the weights of the previous layer multiplied with x of the previous layer, and you add the bias that's meant for this layer, so n minus 1. And so ta-da, we're done. And that's basically just the feed forward using matrix notation and vector notation. So you guys have gone very far knowing nothing from neural networks to now understanding matrices, vectors, how to use them. And next, we're going to look at the cost function and gradient descent, and we're going to start learning about multivariable calculus, but it's going to be a fun ride. So stay tuned. Alright, so thanks for watching. If you like this content, like, subscribe, do all that good stuff. And in the next video, we're going to look at the cost function as well as gradient descent. So stay tuned.